Okay, section 10.4 is the cross product. So we first need to understand the concept of a determinant. Okay, so a determinant. We have a determinant of order 2, which should be for a matrix that is a 2 by 2 matrix. Okay, the determinant of a 2 by 2 matrix is just A times D minus B times C. Okay, your determinant of an order 3 matrix is that was order 2. Okay, order 3 is a little more complicated, and the notation tends to be different. Okay, pretty much a 2 by 2 matrix determinant, we use that A, B, C, D. 3 by 3, we use A1, A2, A3, B1, B2, B3, C1, C2, C3. Okay. Now, the way that you want to kind of think about this is, I'm going to use a highlighter for this a little bit here. This will be fun. We'll try this. Okay. You start with your first column. Okay. And then also think about going across the top row. Okay. And then you want to do the determinant of the four that are left that make up that 2 by 2. So like right here. Okay. And you keep that A1 out front. So let me use what that's going to look like is it would be A1 times the determinant of B2, B3, C2, C3. Okay. Then we subtract. Okay. Now I'm going to grab a different color here. We go to our next column, and you always take out that top row. And now you can see what's left is these guys. Okay, so we would do A2 times the determinant of B1, B3, C1, C3. And then this is where it gets a little tricky. We do plus. So you have to remember that the first one is a subtraction, the second one is addition. And then let's grab a different color here. We take the third column, always the first row. So now we're left with these 4. So now we do A3. I'm going to write it down here. A3 times the determinant of B1, B2, C1, C2. So what that ends up being then, we're not done yet. Okay, we'll simplify it. So we'll have A1, and now we do a little 2 by 2, right? So then we do B2, C3 minus B3, C2 minus, now look at the purple part there, A2, B1, C3 minus B3, C1 plus A3 times B1, C2 minus B2, C1. And that is your order 3 determinant, okay? Which is basically how you do a cross product, okay? So if you keep this in mind, when we do a cross product, of 2 vectors, what we do is we take that A1, A2, A3, and we just use those as unit vectors in the direction of X, Y, and Z, right? Those are just your directional vectors, right? And then the vectors become your B1, B2, B3, and your C1, C2, C3. Okay, I am going to do an example for that one, and there are more in the book too that you should follow along with. But if we find the cross product of maybe vector u, which is -1, 2, 4, and vector v, which is -3, -5, 0. Okay, so we would do u cross v, which would be the determinant. And again, we replace that first row with I, J, K. Second row will be -1, 2, 4. Third row will be -3, -5, 0. Okay, so if you want to pause quick and try that on your own, I would encourage you to do that. And welcome back if you did that. Okay, so now remember, we think about covering up the first row in the first column. And we take that little determinant that's left. Okay, so we're going to do, sure. Okay, so we would have your 2 times 0 minus your 4 times -5, right? I'll write it out here. So we're going to have I, oops, I missed my dot there, times 2 times 0 minus 4 times -5. And then remember, the next one will be subtraction. Okay, we'll have minus j times -1 times 0 minus 4 times -3. And then we will need to do plus next. Okay, so plus k times -1 times -5 minus 2 times -3. Okay, so what we end up with, hopefully, we would have, let's see, a positive 20i. Okay, and then we'll have, let's see, -1 plus 12. Oh, no, I'm sorry, 0 plus 12, so 12j. And then we'll have positive 5 plus 6, so plus 11k. Okay, so that would be your cross product of those two vectors. We could write it, that's your linear combination form. Remember, you can also just write it as 20, -12, 11. Okay, what that means, this new vector here would be orthogonal to both u and v. Okay, and what you would find too is if you reverse the order and did v cross u, you would get the same thing, but just the opposite direction. You have -20, positive 12, -11. So there, if you think about it, if you have two vectors in space, here I can just, if I have two vectors, there are two vectors orthogonal to those. One that would be pointing out of the board, one that would be pointing into the board. Okay, so it just flip the signs to get the opposite direction. Okay, so this one is orthogonal. It's one of two orthogonal vectors to both u and v. Okay, a proof for that is on page 560. I would definitely encourage you to follow along with that proof. Okay, your right hand rule is on page 561. So we know that when you perform a cross product, we're going to get a vector that is orthogonal to both of the vectors, but we won't know which direction it is, because there's two of them. Okay, so that's where your right hand rule comes in. And this is on page 561 in your book. Okay, if you are doing A cross B, okay, what you would do is you would put your fingers on your right hand, and they point in the direction of A. Okay, and then you curl your fingers towards B, and you want to curl, and this is curl over the acute angle. So right, there'd be two ways. If I have vector A like this, and I have vector B like this, so I would take my right hand, my fingers, like take your right hand and make it nice and flat, hold it so that you're pointing your fingers in the direction of A. There's two ways you can curl towards B, right? For me, if I hold my hand onto the screen, right hand fingers are pointing towards the arrow in A. If my thumb is pointing up, I curl my fingers towards B, and it's like the shortest route to B. That's at acute angle. I could flip my right hand around so that my thumb is pointing into the board, but then if I curl my fingers, that's the long way to B, right? I want to curl my fingers the short way to B. Okay. And again, I would look on page 561. Actually, it's on 562. I think it's on page 560. Kind of a little bit of a diagram there, but I'll try to post a video or a picture too on Canvas. But in this case, if I hold my fingers, how I have them drawn now, on my right hand in the direction of A, and I curl my fingers towards B, my hand has been positioned so my thumb is pointing out of the board. Okay, so that would mean that A cross B points out. Okay, so I would have the vector that's orthogonal to A and B and is pointing out. Okay, if I did, and really, I mean, it's the first one. Okay, so A cross B points out. So your right fingers go in the direction of A. Okay, if I did B cross A, now I want my right hand fingers to be in the direction of B, and if I'm going to curl towards A in the shortest distance possible, then my thumb would be pointing into the board. Okay, so B cross A points in. Okay, so A cross B will get me the vector that's orthogonal to both A and B and is pointing out of the board. B cross A will get me the vector that's orthogonal to both A and B and is pointing into the board. And the only difference there will be the positive and negative signs on them. Okay. We have another formula using cross product. So in the dot product, we had the formula for the cosine of the angle between two vectors. Cross product, we get the sine of the angle between two vectors. So the sine of theta is the magnitude of A cross B over the product of these magnitudes. Okay, so again, remember in 10.3, we had the cosine of theta is A dot B over the product of the magnitudes. Okay, so same thing, we think about what happens if that numerator is 0. If the magnitude of A cross B is 0, that means that A cross B has to be 0, right? Okay, and that would then mean that the sine of theta is 0. Okay, so you can think about what type of angle has a sine of 0. 0 degrees. or 180 degrees, right? So these vectors are either in the same direction, okay? They can be different lengths, okay, but they're either in the same direction, so the angle between them is 0, or they're like this, so the angle between them is 180 degrees. Either way, they're parallel. Okay. And what that really kind of means is any vector would be perpendicular to both of them. Okay. A couple more things here. Oh, back up. A cross B is the area of the parallelogram determined by A and B. Okay, so if I have vector A and I have vector B, and I put their initial ends together like that, they make a parallelogram. Okay, and we know that the area of a parallelogram is the magnitude of A times the magnitude of B. No, it's not. It's B times, we can do this here. If this is theta, sorry, area of a parallelogram would be base times height, right? Okay, well, the base would be B, the height would be A sine theta. Okay, right? That would be the height. Okay, and then, oops, we got to get the magnitude in there, and then the magnitude of B. Okay, so that's your area. That makes sense, right? So let me back up a second here. Right here, that would be A sine theta would be the length of that. And then the length of this side here would be the magnitude of B. So multiply them together and we get the area of a parallelogram. Okay. And then just remember, too, if we go back up there, A cross B over the magnitude of A times the magnitude of B, that is the sine of theta. Okay, so if we plug that in for the sine of theta, then we have the magnitude of A times the magnitude of A cross B over magnitude of A, magnitude of B, times magnitude of B. So we get all of these that cancel out. Okay, so then magnitude of A cross B is the area of that parallelogram. Okay. We have another thing. I'm going to kind of leave it to you to do in the homework because we're getting a little long on the video here. Your scalar triple product. Okay, that is A dotted with B cross C. Okay, so remember B cross C is going to give you a vector. Vector A dot producted with that vector is going to give you a scalar. Okay, this is the volume of the parallelepiped determined by A, B, and C. Okay, so that would be if we had like A, B, and then maybe C. I didn't want to make it too right angular. E. Okay, so then this would be kind of like that. Okay, so the parallelepiped. So it's it's a six-sided figure where each side is a parallelogram. Okay, and then there are some properties that you should look on page 562 in your book. And again, they prove one of those properties. Some of the other ones show up in the homework. We need to be practicing those so that we can do some of those proofs on quizzes. Okay. Last thing is torque, which those of you who've taken physics have seen torque before. Torque is basically force times distance. Okay, so if you think about a bolt, here I get to draw again. Let's use gray for a bolt. Okay, so if you have this little bolt, okay, and you're going to, oh, this is fun. Okay, and so let's get the threading here. Okay, so we got a bolt. And we're going to try to unscrew this bolt. So you get your wrench out. Oh, I don't want to use gray for the wrench. Let's see. Make it like a rusty brown wrench. Let's do that. Okay, you get your wrench out. And you get your wrench situated around that bolt. Okay, maybe the handle on the wrench. Yeah, might not have done the best job there. Okay, so there's your wrench. And you're going to use your hand to turn that wrench. Okay, so first of all, you want to apply a force to that wrench. Okay, as far down the wrench as you can. Like it would be silly for us to apply a force up here, right? So you want to apply it far away from the bolt, and obviously you want a big force, okay? And that will maximize your torque then. So if we want to get a greater torque, we need more force or more distance there, okay? And it's kind of fun how that physics works, right? So what we do here, we're going to use a little bit of a different symbol. Torque is a vector, and it's a cross product of, this is your distance vector and your force vector. Okay, now your distance vector is going to be this guy right here. So it basically goes from the center of your rotation, okay, to where your force is being applied. And so there would be R. And then your force vector, I'm just going to put the initial end where the position terminates. Okay, and there's your force vector. Okay, so your torque vector then, if you can think about it, it's the cross product of R and F. So use your right hand rule, right? Your right fingers down R, curl them towards F. Think about F as being right here, because that right hand rule works when the initial points are the same. So you would right hand down R, curl towards F. You have to have your thumb pointing in. So that is your axis of rotation. Okay, so your axis of rotation would be pointing in towards the bolt. Okay, so there would be your torque. Oh, why did I do that? I mixed up the symbol there a little bit. Ooh, redo. It's getting a little glitchy. Tau, right? Okay, so your torque vector, which would be the cross product of your position and your force vector, will point in towards the bolt. Okay, and you kind of get that, like when you're using a wrench, you don't pull out on the wrench. If anything, it kind of feels like you're pushing in. Okay, the magnitude of your torque vector. Why do I keep missing that? The magnitude of your torque vector is the magnitude of the cross product of R and F, which is also magnitude of R, magnitude of F, sine theta, right? Just by your formula, right? Because your sine of theta would be magnitude of R cross F over magnitude of R, magnitude of F. Okay, so that's, two ways to figure out the magnitude of your torque. This way, we have to do a whole cross product to get there. This way, easier. Okay, so if you want to figure out your torque, you would use that second equation. And I should clarify too that theta is the angle between your two vectors there, your vector, your position, and your force vector. So there's theta. That's also theta up there. Okay, and that's it for cross product then.